Welcome to the Jack Westin MCAT Podcast with your host, Phil Hawkins.
And Azaii Calderón Muñiz.
Welcome, everybody. Now, Azaii, I don't know about you. I got up this morning. I went and got my coffee. I was like walking around in the park, drinking my coffee. I felt a little basic. Thank you for laughing at that. Today, we're going to be talking about acids and bases. This is obviously a really important topic in chemistry, but also in biology. There's a whole lot of ways that understanding pHs and understanding pKa's and like how acidic and how basic things are change how your body deals with medications, changes how your body deals with different proteins, right? There's all this acidosis and alkalosis, which are like diseases where your pH is off, like your blood is too acidic or too alkaline on the other side, too basic. I got too basic of blood. I was walking with my foster daughter the other day, who just started college, and she was wearing like leggings and drinking Starbucks, and she's like, I feel so basic. And I'm like, and in my mind, I immediately start thinking about chemistry. So maybe that just makes me a nerd, in case anybody was wondering about that. But
we'll take you as you are.
Yeah, I'm glad this is a welcome home to nerds and people who like learning about science stuff and how it relates to medicine and the world around us. But I feel like the first place to start with this is just like, what's an acid, right? What's a base? And strangely enough, that's kind of a hard question to answer, because there's like different definitions of acids and bases. And not only are there different definitions, but you got to know the different definitions. Arrhenius, Bronsted-Lowry, Lewis acids and bases all exist for all three of those categories. I always like to think about it in terms of like the simplest definition. Like, what do we tell a middle schooler about acids and bases? What do we tell a high schooler? What do we tell a college student? And as you grow, your definition kind of changes a little bit more, becomes a little bit of a better definition, technically, encompassing more exceptions and things like that. But I feel like whenever we start off learning about acids and bases, it's just like acids have hydrogens and bases have hydroxides. So like HCl, that's got a hydrogen, it'll give it away, so it's an acid, hydrochloric acid. Sodium hydroxide, NaOH, that'll give up the OH, that makes it a base. And so this is the Arrhenius definition. And in case you're ever wondering, like, how do you keep track the different definitions? It goes alphabetically from the simplest definition to the most complex definition. So Arrhenius is the first one. And it's just anything that gives up a hydrogen or gives up a hydroxide will be an acid or a base, respectively.
Yeah. So before we kind of keep going, the moment you started talking, I had completely forgotten about this. For my application to undergrad, I went to U Chicago, and they would do these kind of fun prompts. And I remember the prompt that I answered was, what would you be, an acid or a base? Don't be neutral in your answer. And like that was actually our prompt that year. So it just brought back so many memories. But yeah, so I like to think of acids and bases, right, in terms of chemistry class in high school, because I don't know about you guys, we did lots of titrations, right? And sometimes we worked with things like hydrochloric acid and also sodium hydroxide, definitely lots of traditional bases. But like you were saying, as we kind of start graduating, right, we get more complex definitions, and the Bronsted-Lowry definition expands a little bit more. And so now we still have acids that are proton donors and hydrogen donors, but we get a little bit more creative with our bases. And our bases can now be not just giving up hydroxides, but accepting protons, right? Accepting these hydrogens, which should make sense, right? Because if an acid is giving one up, then a base should be willing to accept it. So pretty straightforward. This changes what we can call an acid or a base. And this is a fantastic place for the MCAT to test you on this. They might ask you, which of the following is, right? Or like give you a passage with some of acids and bases and, what type of acid or base is this? So something like ammonia doesn't have hydroxide, right, to give up. But we know that it's a base. And we know this because it fits the Bronsted-Lowry definition, even though it doesn't fit the Arrhenius definition, right? So we know that it can accept a proton. And so NH3 becomes NH4 plus. And so as we graduate our definitions, we also get to consider more things, acids and bases, which is very helpful, not just for the MCAT, but also considering, right, what happens when you have these interactions and reactions. And you probably worked with, you've probably seen ammonia on, household cleaning products. And I don't know if we actually use them for titrations, perhaps not. But I know we definitely worked with more than just sodium hydroxide. And so having that expanded definition is useful and something that you definitely need to know for the MCAT.
Yeah. So essentially the Arrhenius definition is not a great definition of an acid and base. It's just something that if you're talking to a younger audience and you're trying to help them learn, just like the simple, most common acids and bases, the Arrhenius definition is good enough, right? It's okay. So we'll do that. But you're right. Like ammonia is a classic example of a base, right? Especially within the realm of medicine, right? Thinking about like NH3 picking up a hydrogen, becoming NH4, like that is a base because it's decreasing the number of hydrogens in my blood, in my wherever in my body. We pee out ammonia. That's actually one of the ways that we control the pH of our blood is by peeing out like ammonia and controlling like the hydrogens by like taking ammonia, making ammonium, and peeing that out once it's like grabbed a hydrogen. And so we can adjust our pH by regulating the amount of ammonia in our body. So obviously it's a base, but also, just kind of like thinking about how the MCAT's going to test this. There's a lot of molecules in our body that have carboxylic acids on them, right? Like fatty acids, amino acids, right? Like all over in our body, we see this. Most of the biological, like basic molecules, basic as an alkaline molecules in our body, have ammonia or nitrogens, amines on them. So like this nitrogen's ability to grab a hydrogen from the environment. That's why like amino acids, like the amino part of amino acid is a base. So like every single amino acid in your body is an acid and a base because it's got a carboxylic acid on it and it's got an amino group. Also, all of your like nitrogenous bases, so like they can actually be like pick up hydrogens, like your A's, T's, C's, and G's. But also, if you just think about like the amino acids, right? Like sticking to that because that is the highest yielding on the MCAT. You're gonna get questions on this. All of your acidic amino acids, their R group is a carboxylic acid. All of the alkaline amino acids, they all have nitrogens on them. They all like histidine, lysine, arginine. They've all got nitrogens on them. I think in the case of arginine, it's got 3 nitrogens. But that's why those things can act as bases, why they're basic amino acids as an alkaline, is because of the ammonia. And Arrhenius definition just doesn't address that. According to Arrhenius, that those aren't bases, but they are definitely bases. So yeah.
And as we kind of keep going, we're also going to see that this idea of the structures becomes really just becomes even more important as we change our definition, because it may not feel like, you might think, okay, well, we had the hydroxides, that's the most limited, right? But we have some biological molecules that, have it, but we also just continue to care about this as we broaden our definition.
Yeah. One thing to mention, like you did say, like the definition for acid is actually the same for Arrhenius and Bronsted. Something gives up a hydrogen. But the Bronsted-Lowry is a hydrogen acceptor for a base. I want to be clear that like sodium hydroxide, which is a classic base, that's like the most basic of bases. Basic is and not alkaline in that definition. This is going to get confusing for people. I'm going to quit doing that. But like something that gives up an OH minus, that OH minus will take hydrogens from stuff. So every Arrhenius base, something that puts out hydroxides, those hydroxides will accept hydrogens. So every Arrhenius base is a Bronsted-Lowry base. But there's also things like ammonia, which are Bronsted-Lowry bases, but are not Arrhenius bases. So the Bronsted-Lowry definition is just straight up better. I feel like when students start learning about acids and bases, like middle school, high school, you learn about like the Arrhenius definition. College, you start to learn the Bronsted-Lowry, and maybe in college you also learn the Lewis definition. But that also all of a sudden, like I feel like really understanding Lewis acids and bases is kind of a like I feel like only the best college students actually understood that. Maybe I'm like showing myself a little bit too much in this, but like the first time the Lewis acid and base was explained to me, I'm like, I don't understand it, whatever. And I'll just like move on. Like they just tested the definition and I memorized the definition and I didn't really understand. But there are things that are acids and bases that don't fit the definition of the Bronsted-Lowry or the Arrhenius. So there's a better definition out there. And so Lewis is all about Lewis structures, right? Like seeing like the electron pairs or lack of electron pairs. And so the Lewis acids and bases are based on electrons, like something that donates or accepts electrons. And here, like it's actually flipped. So the Bronsted-Lowry acid is a hydrogen donor. The Lewis acid is an electron acceptor. So it's actually going in the other direction. And the base is going to be an electron donor. So once again, just to be clear, like looking at ammonia, right? Ammonia's got this extra pair of electrons. It's got like NH3. So it's got the 3 hydrogens and then it's got a lone pair. That lone pair can react with an H plus in the environment. And so that reaction of grabbing a hydrogen is actually this electron going out and grabbing and creating a bond to a hydrogen that didn't exist. And so ammonia is a Lewis base also, just like Bronsted-Lowry. But there's something even more complex. And this is where like most students are not going to catch this. And this is why it's a really good MCAT topic. But if you look at something like boron trifluoride, so most people are like, wait, what? That is an acid. There are no hydrogens on boron trifluoride. Like it's BF3. It's a boron with 3 fluorides attached. And so most students are going to look at that and be like, wait, how is that an acid? Right? So the interesting thing about boron trifluoride, it's kind of the opposite of ammonia in that it's got these 3 bonds to fluorines, but then it's got an empty orbital, right? It's actually, it doesn't have an octet of electrons. It's got the 3 bonds and then that's it. It really wants to form a bond to something else. And so if you put boron trifluoride into just water, what happens is water, some of the electrons on the oxygen will bond to the boron. And so the boron all of a sudden gets an OH attached to it and the other hydrogen falls off. And that hydrogen that falls off is an H plus. So by adding the boron trifluoride to the water, it reacts with water to like take the OH from the water and attach it to this molecule and leave an H plus behind. So if you were to take a big handful of boron trifluoride, throw it into the water, it's going to be a very acidic solution because each boron trifluoride is going to react with water to create H pluses in the environment. So even though it doesn't have any hydrogens on it, whenever you throw it in water, it creates hydrogens via reactions. And so boron trifluoride is an acid, right? You put it in water, it's an acidic solution. And so that's one of those like kind of weird ones, right? That kind of doesn't hit this classical definition, right? Like I've met with, I have so much to say. I've met with a ton of students and talked about acids and bases. I think very few of them have had a really good understanding of Lewis acids and bases and like why boron trifluoride is a Lewis acid and why ammonia is a Lewis base. Note just something interesting that like to just kind of take a second and step into an adjacent realm of chemistry. Whenever you have two things reacting. Like let's say you had ammonia with the extra electron pair and boron trifluoride, which has the empty orbital. Those will actually react with each other, where the electrons from the nitrogen will form a bond with the boron. That's a neutralization reaction because that's an acid and base reacting. And I think a lot of students don't see that as a neutralization reaction. But not only that, but that's a really specific, interesting kind of bond that forms that the MCAT really likes to test, where both electrons came from one thing, and it formed a covalent bond. And so we call that a coordinate covalent bond, where both electrons came from one thing. Compared to a carbon and a hydrogen, very often they'll form a bond and they both donate one electron. This is something where the nitrogen is donating 2 electrons to form the bond with the boron. And so that is a coordinate covalent bond. And it turns out that literally every single time you form a coordinate covalent bond, it's a Lewis acid base reaction, because that donating electrons, accepting electrons, that's the definition of a Lewis acid and Lewis base. And so that is by definition a neutralization reaction. And the MCAT could test that topic. And so just link those two ideas together, like a coordinate covalent bond and Lewis acid base reactions, because they're actually the same thing.
For anyone that's listening to this and is anything like I was in terms of a college student, I know that this can be tricky. And so writing it out when you have an opportunity can be super helpful. Draw out those bonds, follow the electrons, right? When you're studying organic chemistry, which you also have to study for the MCAT, right? We tell you guys, follow the electrons. And so with acid-base reactions, specifically with Lewis acid-base reactions, that's where following the electrons can help bring those light bulb moments. And so one thing, just to kind of make sure we're keeping track of all of our definitions, I like to actually remember the definitions by Abel. So Arrhenius, most basic. Oh gosh, here we go again.
Yeah.
The simplest, right? Then Bronsted-Lowry, then Lewis acid. And the way I think about this is you are able to memorize the definitions. With Lewis, right, being at the end, electrons. And I like to do this in concentric circles. So 3 circles, one inside the other. The tiniest circle, Arrhenius. Slightly bigger circle, that includes the Arrhenius, Bronsted-Lowry. The biggest circle, Lewis, right? So anything that is an Arrhenius acid is also Bronsted-Lowry acid, is also Lewis acid. But like we were saying earlier, you have this whole realm of Lewis acids and bases that don't meet the other definition. So that's kind of that white space in the largest concentric circle.
Yeah, I like thinking about it like that, because I think this topic would be really good for a Roman numeral question.
Yes. Oh my gosh.
Where they're asking ammonia, is that a Lewis base, Arrhenius base, Bronsted-Lowry base? And it's the Bronsted-Lowry and the Lewis, but it's not Arrhenius. And so understanding which ones fit inside the other ones is something that you definitely should know, because I think that would be a really easy question for the MCAT to write.
Yeah. And even when you think about how you approach this question, right, you're going to actually want to start with the simplest, the simplest meaning not the most basic, but the one that encompasses the least, because if it encompasses that, the other ones have to be true. Right. And so that's another way, a way of being strategic in how you're answering questions and approaching questions on test day in the sciences. Of course, there are plenty of ways to be strategic in cars as well, but in the sciences, this is how we're going to do that. Something else that is important to note that we haven't explicitly said, we're not going to go into this, but you also should consider how the different structures and the way that we approach these structures in organic chemistry will impact the acidity or how basic something is. So for example, this idea of electrophiles and nucleophiles, right? So they want something. So nucleophiles want this positive charge, thinking nucleus. Electrophiles want the electrons. And so thinking about acids and bases, right? Nucleophiles, generally speaking, there are exceptions. You can go look some of those up, but nucleophiles will be Lewis bases, because again, a Lewis base donates electrons. So they are looking for that positive nucleus, right? That positive partial or complete charge. And so that's helpful to make sure that you're keeping track of when you have a reaction or when they discuss something, because even in a Roman numeral question, they could also, if they really wanted to be mean, throw in an idea of electrophiles and nucleophiles. You also want to consider, and again, we're not going to go into the specifics of this, but pull up a periodic table. Think about how going across a period or down a group would impact acidity, how resonance impacts acidity, right? We talked about how carboxylic acids, right? They're an acid. So what does the resonance have to do with their ability to donate that proton and handle, kind of a leftover negative charge? And so having this discussion has made me realize I really miss teaching the sciences. We were just talking about this earlier. But you can still keep things simple in the sciences and like as a way to start understanding them and then build off of that, right? Yeah. So draw these things out, explore that, and it can also make just orgo more bearable if you have a concrete foundational understanding.
Yeah, that's a really good point. And like students always, when they're studying, should be thinking about how do I connect this to other stuff, which is why like in the course, we're doing that all the time. But like, how the definition of a Lewis acid and Lewis base, how does that relate to coordinate covalent bonds? How does that relate to the strength of a nucleophile? How does that relate to like resonance, and how does that affect the strength of an acid or a base? And so all of those are things that you want to be looking for those connections. And so you have to kind of understand it at like a very, very efficient level at the beginning, like at the foundational thing. Don't be like me and just memorize the definition of a Lewis acid and base. Like, I don't actually understand it. I just know electron acceptor donor, and like that's it. But like actually understanding how this works and like how boron trifluoride added to water makes it acidic. And like that's weird, right? If you have just memorized definitions.
You essentially need to get a third grade understanding before you can move on to high school and college and fill level mastery of these topics.
That's an inside joke. If anyone has been to one of the free trial sessions, Azaii talks about this. Yeah, like trying to read like a third grader. Also, we just came to the conclusion that she's a third grader.
Because I'm a third year in med student. So I'm all around a third grader. Personality, approach to cars, med school. But I really do believe that having that, strong, simple foundation will make these complex topics more easier, not more easier. See, there's that third grade, that third grade component. Speaking of strengths, right? We want you to get strong at understanding acids and bases. We also want you to be able to understand the strengths of acids and bases. And this is where we don't want you guys to just memorize the definitions. We want you to understand them. You do have to just memorize some of the acids and bases in terms of which ones are strong and which ones are weak. That said, you should still be able to, once you've done that, understand why they are strong and why they are weak. All right. So some of the strong acids that you need to know, we're going to list them. Y'all know I'm not a big fan of lists, but we need to list them. So hydrochloric acid, right? HCl, hydrobromic acid, hydriodic acid. You're going to need to know, hydrochlorate. I had to think about that for a second.
Yeah.
It's been a while, you guys, but you want to make sure that you're also understanding like what happens. So for example, with hydrochloric acid, we're releasing the protons into the solution. The same thing is going to happen, and I'm going to need you to help me out with this one. I have completely forgotten it. H2SO4. You can also tell
sulfuric acid.
There we go.
So I think there's like 6 main strong acids that like you want to have those down. So it's HCl, HBr, HI, hydrochloric, hydrobromic, hydroiodic, sulfuric acid, H2SO4, perchloric acid, HClO4, and nitric acid, HNO3. And so those are the 6 that I would just memorize as strong acids.
You can tell that I was a student that memorized the written form. don't be like me. You actually do need to remember, it's been a while. You need to remember the nomenclature, like the naming rules, because they could be mean and give you the name, but not the
They
structure.
could say like you reacted perchloric acid, and they don't actually tell you the structure of it, but maybe you need to know the structure in order to balance a reaction later on.
Yeah. And you also, again, want to just think about why this is the case, right? So again, you're just, in the simplest definition, you're thinking, what's going to happen with that proton, right? Even though sulfuric acid, my like base reaction is H2SO4, I'm going to have to stop that. But you want to think about what's left over, right? So in both cases, you are giving up a proton, but in this case, you're going to be left with a negative charge. And so it's going to be harder to give up that second proton, right? So that, I didn't expect to go into this. The conjugate. So you have this strong acid, right? What you're going to be left with is a weaker acid, and it's going to be a stronger base, right?
Yeah.
Than the sulfuric acid, I'm going to keep saying it, the H2SO4. So
Right.
That's something else that I don't think we were initially planning on talking about, but that you want to make sure that you understand, right? An acid and its conjugate base, a base and its conjugate acid, just meaning what you're left over with after that acid or base reaction occurs, and how starting off strong can leave you with weak, or vice versa.
That HSO4 minus that's left, the conjugate base of sulfuric acid, that's what we call an amphiprotic species. Amba meaning like both, right? Like ambidextrous is both hands. Amphipathic means it likes like hydrophilic and hydrophobic solutions. Amphiprotic means it can gain or lose a hydrogen, right? HSO4 minus can pick up a hydrogen, become H2SO4, or it can lose that second hydrogen, become just sulfate, SO4, 2 minus. After you lose that first one, you're right, like you're left with HSO4 minus. That whole thing has a negative charge. It's really hard to pull the second H plus off of that because the whole thing has a negative charge, and like, negatives and positives attract each other. It's hard to pull a positive charge thing off of something that's already negatively charged. The MCAT likes to ask this with sulfuric acid, but also phosphoric acid, right? Phosphates are all over in the body. And so H3PO4, the first hydrogen's pretty easy to pull off. The second one's harder. The last one's pretty hard to pull off kind of overall. And so having a good kind of understanding of what's going on with that. One other thing I want to kind of like clarify is we make assumptions when it comes to strong acids, right? Like we always say like, oh, it completely dissociates, right? It doesn't really. Like hydrochloric acid mostly goes forward. Like if you had 10,000 hydrochloric acids, 9,999 are going to go forward, but one of them is going to stay as a hydrochloric acid. But we round all over on the MCAT. And so we just say like, okay, like it just all goes forward. It doesn't actually all go forward, but we pretend it does. And so that's something to note, that there are scenarios that if I had hydrochloric acid in a solution and 99% of it goes forward into H plus and Cl minus, if I just kept throwing hydrogens in there, like over and over, like making it really acidic, that's adding product to that reaction. It's going to shift it backwards. So you actually could have a solution that's all HCl and no chloride in the water if you just kept adding hydrogens. That can shift it back. And so I think students want to say that it's always going forward and it always goes all the way forward. But there are scenarios where that's not quite true. And kind of understanding that is a little bit tricky.
Yeah. So you said something, and I want to make sure we mention it. This idea of if we add more product, right, the reaction not moving forward as much is tied to a really important topic on the campus section, and that's Le Chatelier's principle. So you also want to make sure that you understand this relationship between a reaction moving forward or backwards based off of how you tweak the products or the reactants, the concentrations, recognizing that the goal is to return to equilibrium in this, right? But if you haven't already studied that, you're going to want to make sure that you understand that as well. It's a high yield topic.
Yeah, super high yield. The other thing I want to mention, so there are some weak acids I think students should know also. Probably the highest yield acid, period, on the entire exam is carbonic acid. And if you're anything like me in undergrad, I don't think I ever heard of carbonic acid because it just didn't come up. We never used that in labs. We never used that for things. It's really important biologically, right? So this is H2CO3. It's a weak acid. It's also what is formed in your body whenever you combine water and carbon dioxide. And so you probably heard, if you're deep into studying, about the carbonic or the bicarbonate blood buffer system. Bicarbonate is the conjugate base for carbonic acid, right? Carbonic acid is H2CO3. After it loses one hydrogen, just like sulfate, it becomes a negative charge. So it becomes HCO3 minus. Now we call that bicarbonate because it can go in both directions, right? It can gain a hydrogen or lose a hydrogen, just like HSO4 minus can. It's in this weird thing where it can act as an acid or a base. But carbonic acid shows up all the time. Like if there's ever a passage in the Chem Phys section that mentions carbon dioxide and water, there's going to be a question about carbonic acid, and they really like to ask that. Just a side note, just like from something kind of interesting in the outside, I think we talked about this in the psych section. We talked about taste, but we have our sour receptors in our mouth react with acids. And so if you have water and you throw carbon dioxide into that, it makes it weakly acidic because it forms carbonic acid. And so carbonated water, or like LaCroix, or, Dr. Pepper or Coke or Pepsi or whatever, Sprite, notice that those things taste different after they're flat. And that's because that carbon dioxide can leave the water. And when it does, that makes it, like, that carbon dioxide in there makes it acidic. When it leaves, it makes it less acidic. And so that actually changes the taste because of how it affects the sour receptors in your mouth. And so that's something to just kind of like understand and connect, like, oh, that's carbonic acid is why pop tastes the way it does.
It's also why it's not great for your teeth and your enamel.
Yeah, because it's
this acidic component. So even though this is why some people with sensitive teeth, even though there's, really no sugar in something like LaCroix, right? I don't think there is. I think it's So these flavored seltzer waters, you might actually still notice some sensitivity because it's weakly acidic. I want to pause and point out that carbonic acid is part of why it's also really high yield. Is it's a huge connecting point across different topics. So it can come up. This is where knowing where things can come up can be helpful. It can come up with, right, acids and bases and buffer systems. It can come up, they could do like a titration curve on it. It can come up with the respiratory system because of its relationship with carbon dioxide. It could come up in the circulatory system. Again, it just depends, right, what they decide they want to test you on. We are right there, already have two sections that carbonic acid can come up in. They could also use it with respect to enzymes because carbonic anhydrase is important.
Yeah.
And so there are so many different places and so many different topics that this one acid can come up in. And I think as a student, it was helpful to know where to expect things, because then as I was reading a passage and I got an idea, okay, we're talking about this, so I might get questions on X, right? Or I might get questions on Y. Having that ability to recognize the topic and related topics made it feel like we have just a little bit more control over this very wild exam, and understand and be able to predict, okay, what might they ask me about?
Yeah. Well, another thing with the enzymes, like absolutely carbonic anhydrase gets tested a lot, which is an enzyme in your red blood cells that helps you make bicarbonate or carbonic acid. But also, like, your cells, when they get really active, make a lot of CO2 when they're like really metabolically active. That CO2 can react with water inside your cells. It happens way better when you have carbonic anhydrase, which facilitates this reaction, but it happens anyway. And so your cell's cytoplasm actually becomes more acidic when you are exercising, right? Like a muscle that is exercising, that cell becomes more acidic due to that and lactic acid. But the pH inside your cell changing can also affect proteins and enzymes in terms of changing their activity. There are certain enzymes in your muscle cells that work better when it gets acidic. And there are certain ones that work worse when it gets acidic. And like our body takes advantage of this because there's certain enzymes that are more important when we're exercising and like they get slightly more efficient in these cases when you're exercising, which is also like another way to tie pH and protein folding and stuff like that into this as well. But yeah, bicarbonate, I said there was a couple of weak acids you need to know. And like we just talked about carbonic acid because that is easily the highest yield. The other one to be careful of is hydrofluoric acid. And that's because when you look at the halogens, right? You look at like chlorine, bromine, iodine, fluorine, all of them are strong acids except fluorine, right? Hydrofluoric acid is a weak acid. So that's kind of a weird exception. And so you should know that hydrofluoric acid is a weak acid overall.
Yeah, this was something I struggled with so much because I was like, why on earth is it a weak acid, right? Because, okay, if it's really highly electronegative, wouldn't that make it a great one? But you also just think about hydrofluoric acid, right? It's so that fluorine is smaller and it is very electronegative. And so it has this really strong electron density, right? All those electrons, all that negative charge, is there. And so it's going to make it like that more concentrated density is going to make it harder for it to handle any, again, just thinking about, for example, our Lewis definition, right? We said that an acid is an electron acceptor. And so you try and give it more electrons when there's already high electron density, it's going to be mad. I like to personify the sciences, yes, in case you haven't noticed. But I think sometimes when you find that weird exception, you're like, I really have to understand what's going on. Sometimes taking the step to understand what's going on can help reinforce the topics that you're struggling with. So that's why I just wanted to pause and touch base on that a little bit.
Yeah, absolutely. And that's why in the class, every time we lecture on something, we talk about how is this connected to other topics, because that's how the MCAT tests things. They don't just like, here's a chemistry passage where everything's chemistry. And it's like, no, here's a chemistry passage that also touches on neuro and respiratory and enzymatics and protein folding and everything else. One thing I know students struggle with this. Students like to categorize things. People like to categorize things. I like to say this is good or this is bad, right? This is a strong acid or a weak acid, right? And we like to categorize, right? Like putting things in boxes. This is an alkaline amino acid. This is a hydrophobic one. This is a polar aromatic one. This is a non-polar. And so we like to make these classifications, but very often things are not just straight boxes. It's like a spectrum, right? And so in terms of a strong acid and a weak acid, it's really more of a spectrum. I always like to use the analogy of like, what's a strong acid? What's a weak acid? That's kind of like what's a strong person and a weak person, right? Like everyone is going to agree Shaquille O'Neal, strong person, right? Or Thor Bjornsson, which is this like Icelandic like bodybuilder. He's a strong person. I think he was the strongest.
Or just Thor.
Yeah, or just actual Thor. I feel like anyone named Thor has to be strong. It's just given. A toddler, weak person, right? Like a 3-year-old, like they are weak, right? But where does a regular person go into that? Or like, let's say just a larger guy that's not Shaq or Thor, but like, are they strong or are they not? Like it's a spectrum, right? Where do I fall in? I'm stronger than a toddler, but I am weaker than Shaq. And so this is actually how acids and bases kind of work overall. Like everyone agrees like those 6 acids we mentioned, hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, and perchloric. Everyone agrees that those are strong acids. But there's some stuff that's just a little bit weaker than that we would be like, yeah, that's a pretty strong acid. And those are the only ones I want you guys to memorize. There are stronger acids than those even, which we'll talk about maybe here in a little bit. But being able to like understand that it's a spectrum and knowing that the MCAT, like talking biologically speaking, right? Like if we're looking at what's going on inside a human body, phosphoric acid is pretty strong of an acid for what's going on inside your cells. And so the AAMC in a passage might call phosphoric acid a strong acid, or they may call it something in the passage itself if we're talking about what's going on inside of a cell. So note that these things that we're calling strong and weak, you should know them, but you should know that there's other stuff that could maybe go into these categories as well. And you need to be able to adapt, right? You're not going to be able to memorize a list of every single strong acid in order from strongest to weakest, because that is impossible to do, because there's a lot of molecules out there that can lose a hydrogen. Some of them, like ethanol, that can lose a hydrogen. It really doesn't want to. And so that's an incredibly weak acid to the point where we don't even call it an acid, right? If you put your hand in a thing of wine, like your finger doesn't dissolve, right? Like ethanol's in there, but that's not like a super strong acid. But, while we're on that topic of acids being weak or strong, I think a lot of times students get caught up in like trying to determine if something's acidic or basic. They just look at the strength of the acid, and that's not a good way to do it. I can't tell you how many times I've been messaged, less now because it's not a brand new show. Man, I'm old. But when Breaking Bad was on TV, there was one episode where they were trying to get rid of a human body. And so they were dissolving the body in hydrofluoric acid. And like I had so many students reach out and like, hey, that's a weak acid. You can't dissolve a body in that. And I'm like, well, you might be able to actually. Like that's actually a real chemistry thing. And that's because like hydrofluoric acid is not good at giving up hydrogens. But if you have a whole bunch of hydrofluoric acids, like millions, billions, trillions of them, and just some of them give up hydrogens, you can have a whole lot of hydrogens in your water. And likewise, like hydrochloric acid, it's a really strong acid. But if you only have one HCl in like a big container, like that's not going to be very acidic, because that one HCl is going to give up a hydrogen, but there's so few HCl's in there. Like if you took a drop of hydrochloric acid and you threw it in the ocean, right? Like it's not going to like dissolve your foot if you step in the ocean, right? The fish aren't dying, right? Like it's because yes, hydrochloric acid, the individual molecules are really good at giving up hydrogens, but there's so few of them that the actual number of hydrogens released is not that much. Versus if you had like a really high concentration of hydrofluoric acid, like 10 molar hydrofluoric acid, you should stay far away from, because that is a very acidic solution. Even though hydrofluoric acid is not good at giving up hydrogens, 10 molar that's a lot of hydrofluoric acid. And so even if like a fraction of them give up hydrogens, that's still a very acidic solution. And so keep in mind that concentration matters. It's not just the strength of an acid. The concentration also plays a role in how acidic a solution is going to be. And the MCAT knows that students get caught on that, and they like to ask questions about like a really dilute hydrochloric acid solution, and they ask you what's the pH, and it's like 6. And like nobody wants to say 6 because it's hydrochloric acid and that's strong. But if it's dilute, it's not going to be that strong.
Yeah, y'all know we love analogies here. Context is essentially what matters here, right? So if you have Thor, right? We all agree Thor represents the strong acid. And you throw 10,000 third graders or toddlers at Thor, right? They are very weak. Thor's going to have to work a little harder to get through these, 10,000 toddlers, these 10,000 third graders. And so
I like the idea of making them fight, but I feel like you could just do like, how strong are they? How much can they lift? Right? Like how many pebbles can they lift? Like 10,000 third graders are way stronger than one Thor.
I was thinking just like throwing themselves on top of Thor in one giant group hug. We have very different perspectives. But it's also like, you put one of us, average person, and you're trying to just wade through like water, right? Water is not going to put up much of a fight, but the more you have to wade through it, the more difficult that it's going to be. It's also like, let's say that you have a friend, or let's say that you inherit a ton of money, right? Yeah, you have a ton of money now. So you might inherit, let's say, I don't know, $10,000. But then you do fundraising, or like a GoFundMe, or like one of those running fundraisers. And now you have 60,000 people who each give $1. You have more. So the contribution of each individual can be less. Same with the acids, right? The contribution of a weak acid can be less individually, right? Less likely to give up that proton. But net, when you add all of those tiny contributions, you have something a lot stronger, a lot more meaningful, whatever you want to call it, than if just one person was like, yeah, I'm going to be nice today and just give you some money.
Yeah.
Right?
I really like that analogy, right? Like if one person gives you all of their money, they're really good at giving you their money, right? One person gives you every single dollar that they have, compared to a lot of people giving you 1% of their money. Like that second one might be way more money, right? Like if everyone in the world gave me $1, right? I am a billionaire, right? Versus if one person gave me all of their money, I may have thousands of dollars, but like I'd rather have $7 billion, $8 billion. I would rather do that. And so in the case of like hydrofluoric acid, it's not very good at giving up hydrogen, but if you have a ton of it, then like it's going to be a pretty acidic solution. A lot of hydrogens are going to build up, versus hydrochloric acid can give all of its hydrogens, but if you don't have very many of them, it's not going to do much. I really like that analogy. That's a good one. Just kind of like taking and like talking about this. I know we talked about strong acids and weak acids, and I kind of hinted that there were acids stronger than hydrochloric acid, that sort of stuff. I know that the most acidic solution ever created, right? If you guys were to guess, what do you think the pH was? And the most acidic solution that has ever been made in mankind, in a beaker in a lab somewhere. Most of you probably wouldn't say, oh, it's obviously fluorantimonic acid. That is what it is. It's an acid that you'll probably have never heard of, but they were able to make a solution that had a pH of -31, right? That's
wild.
That's a really acidic solution, right? And so that's something to kind of keep in mind. I know we haven't talked much about pH in this session, and so maybe we should address that a little bit more. But just imagining a pH, like something with a pH of -31 is very scary.
Yeah. So like I say, we haven't really talked about pH, but I think it can be really helpful to contextualize what's going on. So with pH, we're essentially considering the concentration of protons in a solution, joining ions. So H plus, H3O plus. And we're saying, okay, how much of that is in there? And specifically, we do it with a reference because we need a reference, right? Mm-hmm. And we do this at 25 degrees Celsius. We need to also, and we need a baseline for this, right? We can't just use some random acid or base to decide, because if we used a random acid or base, our scale could constantly be changing. Mm-hmm. So we use water as a reference. So water will actually autoionize. So we'll split up into, so you have H2O, right? Protons, germanium ions, and hydroxides. And what happens is they're going to split up pretty evenly. We say that then they're going to split up essentially 10 to the -7. Yes, there we go. And so we use that kind of as a reference, so that kind of 7 ends up being a more neutral place. And as there are more protons, it becomes more acidic. Our pH goes down. So something with a pH of 2 is more acidic than something with a pH of 7, right? Because we said 7 is about neutral. Something with a pH of 14 is going to be more basic. Now, this is going to sound odd because we just said that it's with reference to protons, right? It's a log scale. And if you haven't reviewed logs, you're going to need to review logs. But that's why it feels a little odd and maybe a little less intuitive, although most people recognize that low pH, more acidic. Now, you heard Phil say that something had a pH of -31, right? You can have negative pHs because, again, this is just a reference, right? And it's a reference with respect to water. And so you can have things outside of this 0 to 14 range. You also should know for test day that there's a different scale called the POH scale. And so that's when you use hydroxide ions as your reference. And so they can ask you a question. They might give you some information that you can use to calculate pH. And then the question or the answer choices can be in POH. We said that this is all with respect, right? Using the autoionization of water. We know that the max is 14. We know 7 is neutral. What we can do to get from pH to POH is switch with respect to 14, right? And so that's going to help us be able to go back and forth between the pH and the POH scale. And so you have the ability to do that on test day. Don't freak out if they give you something in pH scale and then ask you for an answer choice in POH.
Yeah, that's a really common thing. And I think a lot of students are pretty comfortable with this from undergrad. I kind of want to point out that, so this is actually kind of an equilibria topic. And without getting too far into the realm of equilibria, water will break apart into hydrogens and hydroxides. So if you just have pure water, and you think about how this is going to break apart, right? One water can't break apart into 7 hydroxides and 1 hydrogen, right? It's got 2 hydrogens and oxygen. So when it breaks apart, it's got to be 1 hydroxide and 1 hydrogen. And so that's why the amount of hydrogens and the amount of hydroxides have to equal each other, because that's like asking I took apart 5 cars. How many steering wheels will I get? And how many rest of the cars will I get? 5 cars should be 5 steering wheels, 5 cars. There's no way to break down a car and get 19 steering wheels and 1 car body, right? It's a 1-to-1 thing. So when you break it up, they should be equal. And so the same thing with water. You break it up, you should get 1 hydrogen and 1 hydroxide in that. And so that's why when the pH is 7, the concentration of hydroxides and hydrogens ions have to add up to 10 to the minus 14th for the total amount there. And so or multiply to be 10 to the minus 14th because of the rules of equilibria, which we're not going to go into here, but they do have to multiply together to be 10 to the minus 14th. And so if you have equal amounts of them, then it's got to be 10 to the minus 7th and 10 to the minus 7th. And so that's why the pH of 7 is neutral and the POH of 7 is neutral, which is a measurement of how many hydroxides you have. But you could have a solution that has 100 molar hydrogen ions. So that would mean the pH would be -2 because the hydrogen concentration would be 10 to the second. And so it would be -10 to the minus 2, which means that the POH, which has to multiply to make 14, the exponents have to add up. So if the pH is -2, then the POH is 16, right? Because that adds up to 14. One last thing to kind of mention in on this topic is you mentioned that this is all done with water at a pH or at a temperature of 25 degrees. So it turns out when you change temperatures, things break apart more when you heat them up. And so at a pH or at a really high temperature, you're actually going to get more hydrogens and more hydroxides. And so it's possible to have a scenario where they don't add up, the pH and the POH don't add up to 14 because it adds up to 14 at a regular temperature. If you raise the temperature, they may add up to a different number. It may add up to 12. And so you might have a solution that has a pH of 6 and a POH of 6. I know that's something that blew my mind when I learned that wait, it doesn't have to add up to 14. It does because the KW or the equilibrium constant for water is 10 to the minus 14th, but that can change in response to changing temperature. Oh my gosh, there's so much stuff now that I want to talk about with equilibria, and I know that we're kind of going long here as it is, but that's something to be careful of because the MCAT really likes to see, do you understand this stuff conceptually at a deep level? Because they like to ask those really tricky, weird questions, right? I don't think they're going to ever ask you a question that says the pH is 3, what's the pOH? And the answer is 11. Like that's not going to happen, right? They're going to do something tricky. So they'll say you heat it up and pressurize the water so that you had liquid water at a temperature of 400 degrees Celsius by like upping the pressure. And now the KW is 10 to the minus 12. And so now it's got to add up to 12. And so the pH would be 6 and the pOH would be 6. And like, that's tricky if they give you something like that. So be on the lookout for those sorts of things. There's a lot of times in science that your teachers, I don't want to say they're lying, but they're simplifying things. And so they'll say it always adds up to 14, but it turns out in real life, not necessarily. Just like at the very beginning of the session, we talked about what's the definition of an acid and a base, like the Arrhenius definition. That's the easiest definition to tell like a high schooler or a middle schooler, something with a hydrogen, something with a hydroxide. That's an acid and a base, respectively. But it turns out that that's not strictly true. There are things like boron trifluoride and ammonia that are acids and bases that don't fit that definition. And so that's when we have to kind of expand how we're looking at this and try to understand how does this work in the real world. And your teachers may have fibbed a little bit and simplified things for the sake of just making it easier to learn.
Well, we hope that this podcast expanded your understanding of acids and bases. As always, we really enjoy doing this. And as a reminder, there are so many resources free for purchase at Jack Westin. We encourage you guys to take a look at them. And if you enjoyed this episode, share it with other folks and let us know what you thought, which is always a pleasure.